for identifying the active sites for platinum catalyzed propane dehydrogenation. So let's all welcome Professor Andreas Heyden from the University of South Carolina.
All right, thank you very much for the introduction. So yeah, this talk is about Bayesian analysis and platinum catalyzed propane dehydro, and this has essentially all been done by my PhD student Charles Fricke, and we have an ongoing collaboration with Dr. Sarah John, who is a computer scientist in UNC Chapter. So this title has essentially two parts. One is propane dehydro over platinum, and we just had a number of introductions, of course, on this topic. So briefly, we have this, due to the natural gas boom, we have this retrofitting of the naphtha crackers, so they don't produce as much propylene, so we have a propylene gap, and on-purpose technologies such as the Oleflex process can produce this propylene. And despite the fact that obviously this is a long, for many years, used industrial process, there's still a number of open questions. So this brings me to the second part of the title, which is why Bayesian uncertainty analysis. So this is a computational catalysis talk, and in my opinion, there are some key challenges in computational catalysis. The first one is that the experimental catalyst system typically is highly complex of many different active sites, and we have a relatively complex network of elementary reactions. The next real issue is that even if you have a given active site, and if you have a complete reaction network, computational catalysis predictions usually display a relatively low prediction accuracy. And in my opinion, that directly originates from it being a bottom-up modeling approach. Which you see here, essentially, we try to start at the quantum, at the atomistic scale, and we predict macroscopic reactive behavior. So we go, 15 orders of magnitude at a time, 10 orders of magnitude at a length scale. And we have no fitting parameters, that's the principle, the beauty. But that, of course, comes then with a lot of uncertainties, because we have errors in the duty functional, errors in the approximation to transition state theory. And of course, transition state theory has a free energy, and they are not the energy, so we have to make approximation to go from our energy to the free energy. And of course, we also do relatively simple, usually microkinetic modeling models, where we use usually the Langmuir approximation. So the general idea that I have now in my group already for a number of years is that perhaps you can increase the value of computational catalysis by what I call a combined top-down, bottom-up modeling approach. In a way, you can think of it like a systematic integration of experimental data, but let me quickly say what I'm trying to say. We really don't just want to do from the bottom up, but we also try to use macroscopic, meaning experimental information that directly then affects our atomistic simulations. So quickly, what we're mean with bottom-up modeling and top-down modeling. So bottom-up modeling is a standard DFT modeling that usually we know provides insight. However, rates almost never agree with experiment, and it's hardly possible to know why. And that's the real issue. We don't know why we don't have good agreement. How reliable are actually our predictions? Top-down modeling is what chemical engineers have done for over 50 years, right? You build a model, you fit parameters, and you're pretty good at interpolating between your conditions, but you don't have that much insight, and explanation is very difficult. So again, the fundamental idea that I'm trying to convey here with my group's research for a while is that what we can use this atomistic, this bottom-up modeling, build these microkinetic models, but we just appreciate and acknowledge the uncertainties that we are having. And we just acknowledge, and we do not say we have perfect error cancellation, but we try to get a correlation structure of our errors, and hopefully then we can still make meaningful predictions. And then the next step is that we calibrate our models against the experimental data. So that's where you include the experimental data, which in a meaningful model means that you actually reduce your uncertainty. And then you just use machinery of statistics, where you can now do standard tests like Bayesian model selection. You can then validate against new experimental data, check for consistency, and so on. So the objective of this talk is to identify the active site and reaction mechanism of the PDH or platinum catalyst. The one question is, can one surface facet explain experimental observation? And what does each surface facet do? How does alloying with tin modify our platinum surface? And in principle, of course, I like to present some certain quantification framework for correlated computational models with experimental data sets. So this brings me to the experimental data sets. We're a little biased. We just picked 3 data sets in the literature from the last 45 years. We like those data sets. Again, we're probably biased, but they provide observable frequencies. We like that. That's something we can directly get. Oftentimes they provide selectivity and reaction orders in the current activation barrier. Again, we like to use as much information as possible in our process. Next, again, we follow the standard computational catalysis approach. So we build atomistic models, we study various elementary reactions, we determine free energies, build microkinetic models, but now we have here in red these extra steps. So we now want to consider the uncertainty in our models, particularly we need the correlation structure of our uncertainties, and do Bayesian analysis, and then we use experimental data for calibration and model selection. And in principle, only afterwards we believe it's the same way to do identification of descriptors since we have catalysts. Although this last part I will not do in today's talk. So if we think about a platinum alumina catalyst system, so the first thing we do here right now, we just neglect anything that's related to the support. Okay, so there's no support effect that we consider. We also don't consider metal support interface sites. And we also neglect particle size effects. So, probably in principle it's also reliable for probably particles larger than 2 nanometers or something like this. Although I am hopeful that we can also, the results will be also reliable for somewhat smaller particles. And if you then also neglect corners and then limit us essentially on the 3 most dominant types of sites. So we have 111 facets, 100 facets, and we have stacked down edges. So such as 211 type of sites in this truncated quadrihedral model. So then we look at all elementary reactions. So from propane, any CH, any CC bar, cleavage from every intermediate species. And we do that on each of these surfaces. So we have at least on each surface 46 intermediates and 138 transition states. And then again, we need our theories to get to rate constants. For adsorption, we use collision theory with a sticking coefficient of 1. Of course, the sticking coefficient is not 1, it's going to be smaller, but adsorption is pretty much always this reaction condition in the equilibrium process, so it doesn't matter if it's 1.1 or 0.01, we always get exactly the same result. Then we use transition state theory, of course, neglect recrossing and tunneling. At the high temperatures, tunneling is not an issue. And we believe even if my recrossing rate is, that my rate is decreasing by a factor of 3 or even a factor of 10, that this error is small relative to what we do on the free energy side. So now we need an approximation essentially to go from energy to free energy for 0-point energy and entropy. We do the harmonic approximation where we shift all small frequencies, the smaller 50 wave numbers, to 50 wave numbers that kind of balance our errors and we don't have divergence essentially in our free energy calculation. Of course, this is an error. Okay, so there are much better ways of treating entropy. Very simple ways, such as the 2D free translator, and much more computationally expansive ways, such as complete potential energy sampling, Henry translator models, and so on. And we don't like using some of these approaches primarily because we have so many elementary reactions involved, so many species, and you will see everything multiplies even more in a moment. So that in principle, the only other one that might be really meaningful is a 2D free translator model because that's an easy implementation, right? So if you look how large that error is for propane, ethane, and methane, we did that calculation. We see that error is usually on the order of 0.3 eV. Now it's somewhat a systematic error, so because we essentially underestimate the binding energy, and 0.3 eV is not actually that small, but again, in principle, it should be considered. We don't do it here right now. I somewhat give an argument that yes, we have, certainly if I had propane adsorbed, that's pretty much like a 2D translator because the adsorption energy is so weak. But what matters is not propane absorption. What matters is a transition state, right? The CH transition, the bond cleavage transition state. And I do not believe that that transition state is a true three-trans state. So the truth is somewhere in between. The other issue is it's hard to know the correlation of our errors at just P to the entropy. And hopefully, bear with me for a moment, and then you at least see that perhaps 0.3 is not even our biggest issue. So then we look at field microkinetic models. Again, in principle, we all know kinetic ion color is a much better approach because it permits you to systematically include lateral interactions. Okay? So the problem again is though that then you have to do many, many more DFT calculations to actually be more accurate. Otherwise, you get more or less the same results as the field model. And you might have to solve the master equation with Monte Carlo simulation, which is so much more slower. You will see in a moment that you have to run millions of microkinetic models, so that becomes impractical with kinetic Monte Carlo. We do have to include lateral interaction, so that's a big error otherwise. We use this linear lateral interaction model for many years, still make the Langmuir approximation where the site is occupied and not occupied. And you can think of this linear interaction model as just a Taylor-Series expansion that you cut after the first linear term. But what you see is what we do, we run the microkinetic model initially without lateral interaction. Then we see what are all our high carbon species, everything larger 10%. And now you rerun every species in that environment to then essentially, oh, I have 50% hydrogen. So what happens if I have 50% hydrogen and I have these other species on there? How does this affect my coverage? And then you get this coverage parameter alpha here in that process. So in that way, it's actually many more DFT calculation involved than this that I mentioned previously. So if you now do this with the PBD3 functional and these data set D2, the reaction conditions D2, they're at 793 Kelvin for these three surfaces, and you see here an activity versus selectivity graph. You see, oh, the platinum 1 facet is 4 times as active as the steps, and a little bit more active than the 100 facet. And by the way, I should have more 111 sides. So doesn't this mean everything is essentially the 111 facet that should dominate catalytic behavior? So if you just do the same thing with other good DFT functionals, and I just show you only results for platinum 100, you actually notice that these other very good functionals that we recently developed give us orders of magnitude different activities, and also very different selectivities. So the scan RBB10 gives us more than about 3 orders of magnitude lower activity and only a selectivity of 15%. If we do this for all these different surfaces with all these different functionals, you see a large spread in activity and selectivity. The only thing that's consistent is these diamonds here. So they are all platinum 211. They all predict a high selectivity, although the activity really varies by 6 orders of magnitude. So again, that makes it now hard. Is this 211 actually doing something, or do we have, the 111 that's just so much more active that everything comes from it? So again, this is now the real motivation that we need this Bayesian approach perhaps to still gain knowledge from the system. And that really means what we need is, so we know we don't have error cancellation, otherwise we would always get the same results, right? But we can perhaps still use, get some knowledge about how are these individual energies correlated. And now we can just use these 4 functionals that we just used to get this correlation structure. Or we actually can just use the defined advanced functional that actually comes with the whole ensemble, because it's designed to not just predict an energy, but the distribution of energies within the space of GGA functionals, of course, only. But, we have embedded systems, GGAs, who are delocalized, electrons and metals, the electrons are all delocalized, so that might be just a meaningful approximation. So this is now essentially the graph that shows that perhaps entropy is for us not the biggest issue, because it shows essentially our errors with these 2 different ways of looking at the correlation matrix, so 95 confidence and the median range of 95 confidence, and develop all these intermediates on all these different surfaces. It's on the order of 0.7 eV. Obviously, I said previously our entropy error might be on the order of 0.3 eV. 0.3 eV is not tiny relative to 0.7, but it is significantly smaller than that. And the nice thing up here is now we have the correlation matrix of the errors.
So what we are now doing is we do this standard EFT. Now we use factor analysis from our correlation matrix, and then essentially we run a Monte Carlo simulation in microkinetic models. And then we interpret our results using proper statistics. Okay, so this is going to be, let me see how we do this here. So one thing at this data set number one, this was a low temperature, very low temperature result, and high hydrogen partial pressure. You find the surface is essentially quite selective, and to propylene, no problem here, probably no surprise. And the D2 and D3 are more realistic reaction temperatures, and we essentially find that methane and ethylene become dominant products on the 100 111 surface. But again, this is only the average. But we could consistently find now in both of these correlation models that still the 211 surface always shows high selectivity. So if you look at the surface coverage, again we find at low temperatures and high hydrogen pressures all surfaces are covered by hydrogen, and we still have significant amount of free sites, so that's a pretty good system in a sense. Of course, the temperature is too low to really have a significant equilibrium conversion. As we increase the temperature, the key issues now, it's the 100 and the 111 facet that become really covered by the carbon species. So we believe these are all coke precursors, so it's going to be the coking really originates particularly from the 100, but also the 111 facet where you create all these coke precursors. In contrast, the 211 is showing hardly any hydrocarbons on the surface. So coking should not really originate from that facet. So, but again, when you run this Monte Carlo simulation of microkinetic models, you essentially get distributions, not just mean values. Here you see some of these distributions, one time with the beef model, one time with a functional model. This experimental data set here is the dashed line is often usually you cover the data, but you see you have huge spreads in the predictions, right? Orders of magnitudes and range. So you really have to use some basic statistics to analyze these results to gain real knowledge out of this. So what you then essentially, what we're doing is we calibrate now our models, essentially fitting, but again, you use the underlying correlation matrix of your energies in this process, okay? And then the nice thing is once you have calibrated them, then you can really compare against new experimental data and make real judgments, what is happening on the surface. So again, calibration is just applying Bayes formula. The key thing is when you run it, so our data is actually our frequency, the reaction orders, the time activation energy. And we know the selectivity is between 0 and 1. Our process requires everything go from minus infinity to plus infinity essentially. So that's why we use a larger function of the selectivity as our, which just essentially spreads it out. And again, the nice thing is we get here the evidence at the end after the calibration process. And you have two different models, you can compare those evidences, and then you can say, hey, one model is able to describe the data or another better than the other. So after calibration, again, now you really see we can cover the experimental data. But you see here that even then, in the default scenario for this black line here, that's platinum 100, it's very hard to get to high selectivities. So that service will always have a very hard time giving you high selectivities. In fact, for this functional model, it's impossible to get your experimental selectivities with that facet. You will always have some CC bar cleavage occur on that facet. Again, now we are at a time where we can essentially do statistical tests behind locus distance. So that's essentially just saying, hey, given this distribution of results, given my experimental data set, how good is it possible that I can describe everything at the same time? And again, you essentially fail the test, or you don't fail the test. The bold numbers are where you did not fail the test, so that's a possibility. But you see a lot of other possibilities where you see here. Even though I calibrate against dataset D1 and D2, and then I evaluate it against dataset that I fitted it to, I can still not get the result. So that model just fails the test, essentially. And we know this model cannot describe the experimental data. Again, once we have the evidences, you can look at the ratio of the evidences. And the only thing I want you to remember here is if it's larger than 10, then you have strong evidence of this kind of statistical heuristic, this Jeffrey scale, that one surface is not active, cannot describe the data relative to another sequence. And this is what you see here. Essentially, this is all the ones that passed the Mahalanobis test. And essentially, you see if I fit against data set D1 and D2, evaluate in data set D3, calculate the evidences, then I can clearly say, you know what, only the 2-1-1 surface has strong evidence that it describes it much better. So the steps relative to the flat surface. Again, if I fit it against the other, I have some evidence. And if I fit it against the high temperature data, try to evaluate at the low temperature data D1, then only the 2-1-1 surface is actually able to pass the Mahalanobis test. So it's the only one that potentially can describe the data. So this first part here, what we essentially show is that microlink modeling results are strongly dependent on the EFT functional. For metal surfaces, the correlation structure of the EFT energy uncertainties is better described actually by this B van der Waals functional than just picking good DFT functionals. It's again not surprising given that the B van der Waals functional is specifically designed by giving you the full correlation matrix. But again, the key message here is there's no perfect error cancellation, so we can't just not at all assume that. We find, again, no evidence that the 100 surface can describe experimental data. So again, it might contribute by creating precursors that lead them to a deactivation, but it's not able to actually describe the experimental observation. In contrast, there's strong evidence that it's actually the steps who are responsible for the experimental observation primarily. Although these are not active sites where cooking can really occur, so cooking occurs on other facets. And again, all surfaces, though, can have quite high turnover frequencies at these higher temperatures, and thus one more than one surface could be potentially responsible for the overall observation. And again, this really goes for me that it's also these other surfaces, the 100 and to some degree also the 111, that are responsible for the lower selectivity. That's where the CC bonds are cleaved. And that's also again where you produce these co-precursors. So again, kind of a message here is to improve the platinum count. That's what we really need to do. We need to modify the flat surfaces. It's not that we need to do that much with the edges. It's really the flat surfaces that we need to modify. So this brings me is how does alloying with tin modify the platinum surface? So we know the industrial catalyst, of course, platinum tin catalyst. We see significant improvements in selectivity, and the key thing is coating is, of course, also significantly reduced. And now, based on the previous knowledge, we said we don't need to study the platinum tin system with the four functionals. We can just use the B van der Waals because we just showed that gives us a nice distribution and to get the error correlation. So then we made a decision to look at these surface skin alloys. I know, of course, I don't know how realistic they necessarily are, but it's at least a quick way of looking at how does tin affect the platinum catalyst. And we looked at essentially how you break up the surface so that the ensemble effect is actually different. So you see one for the step, one for the flat surfaces. And you notice that, and you will understand in a moment, we looked at two different ones. One low amounts of tin on the 100 surface and one high amount on that. And again, there are, of course, a number of experimental data out there, but in the following we focus on the study from Barrias, where they also nicely provide turnover frequencies, which is always a property we like to have. And they see there, of course, very high selectivity. So the first thing, what you see here is, let's just start with the 100 facet. We have the standard platinum 100, and then you have these two modified surfaces. The one thing you notice is that small amounts of tin, right? This has only small amounts of tin here, actually increase the mass of the turnover frequency significantly. It also increases the selectivity a little bit, but the selectivity is still pretty low. So that essentially really tells you, oh my goodness, adding small amounts of tin to my 100 facet is actually bad because it increases the rate so much that you have much more non-selective processes occurring. On the other hand, if you really flood the system more with tin, then your activity and selectivity is very similar to the platinum 100 surface, so then nothing crazy happens there more. If you now look here, the same thing for the 1-on-1 facet and the 2-on-1 facet. So one thing you nicely see, the 1-on-1 facet, if you add tin, really becomes both more active, you see more masses to higher values, and it also becomes significantly more selective. So, adding tin to the 1-on-1 facet really does the trick of making it more active and selective. In contrast, for the steps, actually, the mass of the turnover frequency didn't move much, and actually the selectivity decreased. So adding tin to the steps is not necessarily beneficial at all. So the key issue, though, if you look at all these different tin-covered surfaces here at one graph, is you really see this big issue with the 100 facet. How this could really suddenly become the most dominant surface if you only have small amounts of tin on there, which inevitably would lead to a lower selectivity. So you really don't like that. And again, otherwise you see nicely here, just that the 2-on-1 is the one that likely gives you all that high selectivity. So now if you look at the average surface coverage, and again I compare here the platinum ones with the platinum tin ones. Sorry. The first thing is adding tin nicely and cleans the surface, increases the free side coverage. So that's of course very good. The nice other thing is addition of tin dramatically reduces the coverage of the cooked precursors, particularly on the 100 and 1-on-1 facet. So I believe that's one of the key things that tin really does, and there's a way we do it, but you might not necessarily know that it's really the 100 and the 1-on-1 facet that are being cleaned up here in this process. Again, we can of course do calibration again against this data set here, and then we can do our same game with getting evidences and see which surface method might be able to describe the experimental data. And again, just as before, this is always compared to the 1-on-1. You just look at the evidence and take the ratio of the evidences here. You see that ratio is by far the highest for the step side. And it's more than 10 consistently, so we have strong evidence that if it's one surface method that only describes it, it has to be the steps, even when you add the tin. That's the question. So that now brings me to the second part of the conclusion, is that addition of tin cleans the surface dramatically, dramatically reduces the coverage of cooked precursors, and particularly for the 100 facet. So tin really reduces coking. Again, otherwise, of course, we did not include the whole mechanism of forming coke in our microkinetic model, but we believe that a good descriptor for that is just the hydrocarbon species coverage. How much CHC and so on you have on the surface. Next, small amounts of tin increase the activity of the 100 surface. And that's actually a danger, because even though it makes a little bit more selective, the selectivity still remains a variable. So you definitely have to flood the 100 surface with your dopant. I mean, that's absolutely essential. Nice thing otherwise we see is that actually the 1-on-1 facet does become more active and selective in the presence of tin. So tin does another good thing, essentially. But otherwise, it's definitely the steps that are needed to get a high selectivity and activity at the same time. It's the steps that are the only ones that really could describe the overall experimental behavior. Although, of course, we have the other facets at the same time. So let me acknowledge funding. So this work was actually funded by NSF EMR, and in the last couple of years by the iGroup Center, and we used, of course, a bunch of computing resources, and again, all the work has been done by Dr. Fraker, and this is a collaboration with Dr. Tirojano, and I noticed that I'm talking too fast, but that's okay.
Discussion? Sorry.
Really nice talk. So just have a quick question about the Bayesian calibration. So do you use the beef ensemble energy as prior distribution in the Bayesian optimization? And also sort of related, I assume you have a different target property in Bayesian optimization. How do you balance the weight or importance of, for example, rate and selectivity in Bayesian optimization?
So that's a good question. So essentially, it's given here in this likelihood function, right? So you're absolutely right. So we don't actually use the turnover frequencies. We use the tan log of the turnover frequency, so that it's not that everything dominates everything. If you use the turnover frequency or order of magnitude off, you can otherwise get huge differences. Same thing for the selectivity. We use the logic function essentially, but otherwise, again, this is all optimized in the Bayesian process, the sigma. That's the process. So I think to your first question is, we do not directly use the 2000 functionals from beef, but we do also their factor analysis, so that we essentially, factor analysis gives us the distribution so that we can directly work with the distributions, which of course makes the calibration process much easier. Otherwise, it's actually straightforward to just use beef and use a pure forward model, just run 2000 models and done, right? But again, we just run a Monte Carlo simulation there. We base everything on this factor analysis.
Oh boy, there's a whole slew of questions here.
That's good.
Right. So thank you for this illustration of how you use Bayesian statistics. So I presume you look at the forward and reverse reaction first.
Yes.
Right?
Yes.
Yeah, okay. Second, once you've gotten insights that you want the 2-on-1 surface and you want to add tin to the other surfaces, what can you say about deactivation? And something that's not been discussed today is whether deactivation occurs from a precursor on its way to making propene, or is it coming from reabsorption of propene to make propyladiene, which is what the surface chemists would tell you.
So what I didn't show you today, but what we did, we actually also built full particle models, and then run it in a CSTR model. And then we see, to your second point, that sometimes we see the 2-on-1 steps produce propylene that reabsorbs on the 100, and there it gets cracked. And that's, of course, undesired. Now, your first question was, how do we, what's the improve stability with this knowledge? So again, to some degree, I believe some of the, to form coke, we need this coke precursor, we need a relatively high coverage of carbon on the surface. And that's why we just looked at, what's my surface looking in these different environments. And you see, even when we have tin on the surface, you still have actually, I don't know if I have this here quickly, we still have some carbon on the surface. Yeah, I think this is, so this other species is essentially other hydrocarbon species here on the but even on this, you still have 7 plus this C2H2 essentially, and another 4% or 5% just carbon on the surface. So we still have some carbon on the surface. But again, we believe by just looking at the surface coverage of hydrocarbon species, we might be able to ultimately guide the design of more stable catalysts by just keeping that coverage low. That's at least right now the idea.
Thank you for this interesting presentation. Let me see if I understood properly. So you have a nitrokinetic model, and you have also experimental data sets. And now we both and many others know that DFT may have problems with different steps. So taking this uncertainty into account, you would like to find out statistically which statements you can still make about the models you have done. Now, but maybe that there are still models, for example, when you put tin on, I'm not sure how, there may be other models which may also fit the data. This is one point, and the other point is, does this procedure give you a more detailed uncertainty measure which of the steps in the microkinetic model may be most affected by the imperfections of the functional, so that we could then go there and target it, try to improve on the entropy calculation and on the enthalpy calculation.
So let me start with your second question. So what we can still do is do distributions of rate controlling steps. Okay, so we still see here. So this is essentially what we see here. This is actually a pure platinum actually. When you see here, what are the rate controlling steps? And you of course get here. This is the prior crowd calibration. What is rate controlling? And you see, oh, really, most of the things are going to be determined by the first neutron, of course, CH activation. Interesting here, actually, this is the platinum tin case. You see here which, for the 100 facet, it's actually the second dehydrogenation producing this species, which ultimately leads to CC bond cleavage. That is rate controlling there. And now your first question, I forgot right now. So what was your first question?
Different models.
Oh yeah, different, of course. So you're absolutely right. So the only thing, I mean, this is the only thing we can do is we can compare models. There might always be the perfect model that we are unaware of, and that just describes everything. Okay. So of course we are still always constrained by we can only compare two different models. We can just say we can exclude this model. We can never say this is it. We can just say this is not it. I mean that's the only thing. But again, anyhow, so yeah.
One more question. Thank you for the talk. It's quite interesting. Griffin Kenny from Penn State. So I have a number of questions, but to focus it, in your building of the microkinetic model, hydrogenolysis, I didn't see it like a direct hydrogenolysis of carbon-carbon bond. Was that part of the microkinetic model? Did you see like a direct hydrogenolysis as energetically viable?
No, we did not find to be energetically viable. And I was first involved some CH activation, and only afterwards do we see significant hydrogenolysis.
That's very interesting. The reason I ask is that experimentally it's argued about effects of particle size, and I understand that this is applicable really down to 2 nanometers or so, but the rate of hydrogenolysis seems to increase perhaps exponentially. It's non-linear the smaller that you go. So the prediction that these step sites or the increase in importance as you go down is quite interesting. So thank you. Very, very interesting topic.
Next comment. And with that, we'll thank our keynote speaker again.